Good morning. So we are talking about regression today. So we have learned about this in algebra. So we are going to learn about it as it applies to statistics now. So I've sent you these notes. So we're going to use regression to find the equation of the straight line that best fits the scatter plot. The regression line, given a collection of sample pair data, the regression line is the straight line that best fits the scatter plot of the data. So here is what it looks like. We have y hat, which is your response or dependent variable. X is your explanatory predictor or independent variable. And we have BO, which would be your y-intercept, or B naught, I should say. I should say that correctly. And then we have, that's for your sample statistic. And then B sub 1 is your slope. So see how that matches with that. Whenever we put in the calculator, though, it's going to be y equals ax plus b. And that's going to be what the calculator comes up as. And this, of course, goes back to your slope and your y-intercept with y equals mx plus b. Okay. Your equation is going to be where you have b naught as your y-intercept and b sub 1 as your slope. If we're talking about the population parameter, we're going to use beta. That's the symbol that we're going to use. Okay. Our requirements to use regression is that x and y is from a random sample. There is a visual of the scatter plot shows a straight line pattern. And outliers can have a strong effect on the regression equation. So make sure to remove any outliers that have known errors. When we round, we're going to round to 3 significant digits. We're going to use technology TI-84 or StatCrunch that is in my math lab. We are going to make predictions with this regression equation. A couple of things that you need to consider are a bad model, good model, correlation, and scope. So for a bad model, if the regression equation does not appear to be useful for making predictions, don't use the regression equation for making predictions. For bad models, the best predicted value of the variable is simply its mean. Use mean instead. Okay. If we have a good model, if you look at your scatter plot and you look at your regression equation and it matches, then you can use that to make predictions. For correlation, use the regression equation for predictions only if the linear correlation coefficient indicates that there is a linear correlation between two. So remember, with R, we want R to be close to 1 or -1. If it's close to 1 or -1, then that tells us there is a strong correlation. If it's close to 0, 0 is not a good correlation. So let me show you a little graph kind of to represent what the R value should be. Let's see. I'll write it over here. So I'm going to put R values. 0 up until, let's see, 0.413 is a critical value, and negative 0.413 is another critical value. And then go all the way to -1 and go all the way to +1. Let's see if I can show that a little better. Okay, so these are your critical values that tell you there is no correlation. And then from -1 to negative 0.413, there is a correlation. And then over here from positive 413 to 1 is also a correlation. And this can be found in 10.1. Okay. And then you also have to think about your p-value whenever, we're not going to do this by hand, but if you were to get your p-value, for the p-value, because there are some questions in there that give you a p-value, you, of course, want the p-value to be less than or equal to your alpha, which supports the claim of linear correlation. If the p-value is greater than alpha, that means no, not, or how should I write that? Does not, there we go, support the claim of linear correlation. Okay. So you've got to look at the R value, and you've got to look at the p-value as well. Here. Trying to highlight. It's coming back. Sorry. Okay, so let's continue with scope is the next thing. So let me go back over to my textbook. We are going to use the regression line for predictions only if the data do not go much beyond the scope of the available data. So let's say you have available data that is between 150 and 200. If you're trying to predict for 1,000, that's not a good idea. You have to stay within what data you already have, okay? Predicting too far beyond the scope of the available data is called extrapolation. I can't say that. And could result in bad predictions, okay? So if you want to look back at these for more details, you can go to page 493 in your textbook. And your textbook is also on My Math Lab. All right, so let's do an example. So I'm going to look at 469 in my textbook. And it says chocolate consumption and noble laterates. I don't know. Increase the net. Okay, so we have chocolate and we have noble. If a country increases chocolate consumption, is that likely to experience an increase in the rate of the nobles? Okay, so here's the data. We can put this into our calculator and come up with the scatter plot. So let's go ahead and do that. So remember, you go to Stat, Edit, and we want to clear out whatever's in there. That was from last week. And put in our data. So go ahead and do that. So I want to check them as I'm putting in that second one. 8.6, 0.1, 6.1, 0.1, 25.3, 7.6, 6.3, 9.0, 1.6 is 2.7, 1.9, 4.7, 3.3, 1.5, 7.4, 3.9, 1.9, 2.6, 1.7, 5.3 and 10.8. Here we go. All right, so that should match up. Make sure you have that in there. Okay. And we want to graph this, and we also want to do our linear regression equation. So in order to graph it, you go to second. Well, I want to make sure there's nothing in y equals, and there is because I was doing algebra the other day. Okay, then you're going to go to stat plot, and I'm going to turn this on, and it's just going to be a scatter plot. L1, L2, and then I want to go to zoom data, or zoom stat, sorry. And then that is my graph. So we got to check the requirements. Was this a random sample? Yes. Let's see. Random sample. Does it look like a straight line pattern? Yes. Are there any outliers that we know have errors? Not that we know of, no. Okay. So, and this also looks very similar to what was given to us in the textbook. Okay, so now we want to do our regression equation. One thing you do want to check is that on your mode, your stat diagnostics are on, okay? If you don't have those on, you won't get the R. And we need the R to know if it's a good model or a bad model, if it's a real correlation. Okay, once you do that, then you go to stat, calc, linear regression. Okay, so then we write these down, and remember it's rounding to 3 decimal places, so y equals 3 significant digits. 9 x plus, or I should have just put minus 3.37 because I'm rounding. Okay, and then my R value is 0.8. So that's a good linear regression or a good correlation. Also, see how this is positive? If this is positive, then our slope will be positive. Okay. So it's a strong positive correlation is what we can write. Okay, and if you want to write the steps down, you can do that too. I think, I thought there was somewhere I put it. No, I didn't. Yeah, I did. Sorry. It was over here. Make sure you do want to do mode, turn stat diagnostics on. Okay, so that is one thing you do want to do. All right, so now we are going to do the consumption of the 10 kg per capita. So that means that is going to be my x value. And x equals 10 to find what the Noble rate is. So we do y equals 2.49 times 10 minus 3.37. And then remember, the one thing they wanted you to check was the scope. And if we look at this, does 10 fall within our scope? And it does. We didn't go too far above or below. So when we plug that in, so I can quit, 2.49 times 10 minus 3.37. Oh, whoops. I need to go to 3.37. There we go. And that is 21.53. Okay, so that is our prediction. Okay. Okay, and then a few vocabulary things, vocabulary terms. We have marginal change, the amount that it changes when the other variable changes by exactly 1 unit. Basically, marginal change in our case here is your slope. Slope represents the marginal change in y that occurs when x changes by 1 unit. So what is the marginal change in our last example? And that was our slope, 2.49. All right. And outliers and influential points. So an outlier lies far away from the other data points. Influential points, points that strongly affect the graph of the regression line. And we'll look at this page. So this is our original data, and it followed a straight line pattern. That's an outlier, but there are no influential points. But now if you look at this one, look at, this is the original data, but then they threw in this influential point, and that completely changed your line. So you just have to know about these influential points and know whether it's an outlier or influential. If the regression line changes by a considerable amount, the point is influential. Okay. Residual. For a pair of sample x and y values, the residual is the difference between the observed value of y and the y value that is predicted by using the regression equation. So R is your residual. And we've been able to just find it using the calculator, but you can actually find it by hand, which I just want to show you how that's found. It's found by, let's see, residual equals observed minus predicted with that equation. So y minus y hat. Okay, so we'll look at an example of the residual. So if you look at this graph, so this is your observed points, okay? And we were able to, or on this graph, they found the regression equation. And so to find your residual, you would find the difference between what was observed from what is predicted using that line. So there's 11 units that it is, that's how far it's away. This one's -5 units, it's below. This one's -3 units, it's below. This one's +7 units, it's above. So that's how they find their residuals. The least squares property, a straight line satisfies this property if the sum of the squares of the residuals is the smallest possible sum. So if we have our residuals, these are the residuals here. We have the -5, the 11, the -13, and the 7. So you find the sum of the squares. You find them, and you get 364. We can visualize the least squares property by referring to this figure where it shows all of the residuals by their areas. So we did 11 times 11, 11 squared, okay? The sum of the shaded areas is 364 altogether, which is the smallest sum possible. Use any other straight line and the shaded squares will combine to produce an area larger than the combined area of 364. Fortunately, we need not deal directly with least squares property when we want to find the equation of the regression line. Calculus has been used to build the least squares property. Because the derivatives of these formulas require calculus, we do not work through that, okay? It's just so you know the least squares property, how it relates to your scatter plot, and how it relates to your regression line. Okay, a residual plot is found by using all of the residuals. So you plot x and y, where x is your observed, and y is replaced with the residual value. So the residual plot will have the points x and then y minus y hat, which is your residual. To construct a residual plot, you're going to plot each one of these, x and then your residual. And we make our graph, but we want this horizontal baseline at 0 because a good prediction would have a residual of 0. So you're going to have them above and below, just like that last one. It had like 11, so let's say this is 10. So it was at 11 whenever, let's say that's about 12. So let's say this is 10. So it was about 12, 11. The first one was about 8, -5. So it'd be right here. And then the next one was about 20, -13. So let's say this is 20. -13 would go right around here. Oops. And then the last one that's on our plot is about 15 and positive. No, 25, sorry. 25 and positive 7. So this is a residual plot from that data that we got from page 496. So the residual plot does not have an obvious pattern. And it does not be, we don't want it to become much wider or thinner going from left to right. It's just kind of all scattered, but it should be centered on that 0 line. You should have some above, some below. So here's an example of your residual plot. Here is a residual plot suggesting that the regression equation is a good model. Okay, see how it's just kind of scattered. This one's not a good model because see how it follows a pattern? That's not good. And then this one is not a good model because it's really, really close and then it veers off. It becomes much wider over here. So that's not a good residual plot. Okay, and that is it for our notes. All right, y'all have a great day.